Hi, my name is Dr. Anna Scott, and I'm president and co-founder of Project Canary. For those who aren't familiar with Project Canary, we're a Colorado-based public benefit corporation, and we're also really proud to be rated as a certified B Corporation. Before I jump into the talk, I'd also like to thank some of our partners who've made this work today possible, including the National Science Foundation, Caltech's Rocket Fund, Colorado School of Mines, as well as our customers and investors. What we do at Project Canary is provide trusted, independent data. We do this through our TrustWell certification, our rigorous certification process that verifies natural gas has been produced at the highest standards with respect to air, water, land, and community. We then couple this with our continuous monitoring, which uses high-fidelity IoT devices to measure methane and VOCs. Project Canary has been in business for about 3 years now, and today we work with just a little over 30 operators, primarily, but certainly not only in upstream production facilities. Today, we have a network of 200. Over the next month or so, it's slated to be 300 sensors that are located across the DJ Basin, the Marcellus Basin, Green River Basin, the Permian, and we also have some installations in the Southeast US. Sensors themselves send data to the cloud every minute, and this forms the data set that I'll be drawing conclusions from today. This is a picture of what one of those sensors looked like with me for scale at Colorado State University's METEC facility in February. We have two versions, a total VOC sensor, as well as a tunable laser diode absorption spectroscopy sensor for methane. Soon it'll be combined into one. But today we cite these sensors along the fence line of a well pad and include an anemometer at each site. We've recently announced that our data platform is opening up to using other sensors, but for this talk, I'm going to be drawing from conclusions that are just from our sensors. Now, I might be preaching to the choir here, but I wanted to take a second and share why it is that we think continuous monitoring is so important. I see the space of environmental measurements broken down into two critical variables, the first of which is detection limit, and the second of which is frequency. And while detection limit is very important, it's not the only factor. In fact, most emissions are actually intermittent. Here, I'm showing a screen grab of data from our dashboard, and you can see the kind of noise that you get in typical emissions. Additionally, small leaks tend to grow. Here, I'm showing data from what was a stuck dump valve, it was a leak that was found during a blind field trial in conjunction with ExxonMobil and was caught by an operator after about 3 weeks. This was presented at AGU in 2019 by Erin Tullis, where she concluded that high-frequency monitoring can offer faster emissions mitigation as well as insights. And so this is where we see Project Canary fitting in, is in the space of high frequency and relatively high accuracy or low detection limit. To assess how well a leak detection and repair program like this can do in a stochastic sense, I use the Fugitive emissions abatement and simulation model, or FEAST. I calculated the results of a direct detector or continuous monitor program with about a 1 part per million lower detection limit with 3 sensors placed on site. What these results show, the results here show the net present value, is that using continuous monitoring, the gas detected or emission saved, which here is in this dark purple color, exceed those of an automated infrared camera based program or a manual infrared camera program, and do so while actually saving operators money. We've updated these results using the latest version of FEAST. And in this figure, I'm showing the fraction of initial emissions over time as compared to doing nothing at all, which is this light green color of the curve. What this figure shows is that using continuous monitoring for leak detection and repair, when you combine with an OGI camera for follow-up, shown here in the dark blue color, can reduce emissions by up to 80% as compared to initial emissions, and reduce emissions by a factor of 2 compared with only using a camera. In practice, we implement this program by installing 3 sensors on a well pad, as shown here in a live version of our dashboard. The data flows directly to our servers and into this dashboard. To walk through what you're seeing here, we've got a list of sites, we've got our real-time chemical data shown here, as well as wind speed and data, and then an actual map of the pad where this is located at. And in the upper right-hand corner, we have a table of alerts that get issued automatically to producers. They can go into the dashboard, click on it, and see what's going on. And this is driving directly towards what I think we're all after here, which is emissions reductions. So by using continuous monitoring, we've seen operators be able to catch issues fast, whether those are a liquid knockout tank that was frozen, that was caught and remediated within 73 hours, inefficient flaring that was caught and fixed within 42 hours, A vapor recovery unit having pressure issues that was caught and fixed within 7 hours, a thief hatch that was left open that we caught and found within 4 hours. And we all know how often that these happen and how easy it is to fix. Unplanned storage tank venting that was caught and fixed within 40 minutes, to my personal favorite of water hauling emissions due to an oilfield services company not using their vapor recovery lines that we caught and fixed within 10 minutes. And in this case, the fix was firing that oilfield service provider. So sorry, but not sorry. Now this operator is working with an oilfield service provider who does use their vapor recovery lines. And this is exactly the type of issue that simply wouldn't have been identified without continuous monitoring. Now, specifically when it comes to Reg 7 compliance, I wanted to highlight that we've both had to develop monitoring plans as well as automated reporting that connects with our dashboard and automatically generates report. We're finding that this is really critical to the program and saving hours of labor. I know this might not be sort of lessons from fenceline monitoring, but I think this is actually a real hidden gem. So thank you to CDPHE for working with us on developing this. Now, to share some lessons that we think we've learned in the process of putting out all of these sensors. So first of all, and this might sound counterintuitive, but fence line sensor placement doesn't matter. In fact, when you start measuring every second or every minute, we find that the wind shifts quite frequently in the field as compared with those hourly wind roses that I was used to before I started doing this. And so what this means is that you get thousands of measurements even when the wind isn't in the prevailing wind direction. Here I'm showing a windrose from about a week of data at our sites. So this is a radial distribution of the number of measurements of both by number of measurements in the radial direction by wind direction. So that's the direction as well as the speed, and that's the color. And if you look at the least common wind direction, which is this, for example, this north by northeast, for example, you see that there's actually over 1,000 measurements, even though it just looks like there's not a whole lot that you can see. And that's just an artifact of this visualization. In fact, when we start to calculate the number of measurements that we do see, we find that continuous sensors are actually capturing hundreds of measurements from the site every day. Here, I've restricted the analysis to individual emission sources, which are these red and white rectangles on the map, and graphed the number of measurements per day on the y-axis, per time on the right, measurements per day on the top, and then measurements per hour on the bottom. What we find is that it averages out to about 3.4 measurements per hour per each equipment group, in which case, this case, there are 5, which we think is a significant improvement on the quarterly monitoring. Now, you might be looking at this and saying, hey, Anna, it does look like there's some spots where there's low coverage. So we took a look at this. And what we found was that there are a few periods where there's some gaps in the hourly measurements. But what it turns out, the longest gap that we could find was about 6 hours overnight. In this case, the wind was coming from due south. Haven't seen it before, haven't seen it since. And to evaluate the impact of what would have happened on site if maybe a really big emission source had come through, I superimposed a large leak on top of this. That's the plume you see there on the left, using NOAA's high split or the READY API of their high split model. And what this shows is that even if the wind isn't blowing directly, a large leak source will still superimpose on top of your sensor just because of the dispersion. Now, I will in fact roll back my previous statement and say that placement does matter for emissions flux quantification. So here I'm showing data from a calibration experiment I performed at CSU's METEC facility. On the top are the emissions, on the right are the emissions flux estimates from a separator, which was not emitting, as compared to the bottom estimate for the wellhead, which was emitting at about 0.1 grams per second. And what you see is that this purple sensor here misidentifies the leaking separator and confuses it with the wellhead. To illustrate why this is, consider an example of wind coming from the southeast and a detector sitting both behind a wellhead and then a tank. For a given concentration, it's actually not clear if this detector is seeing a large leak source coming off the tanks or maybe a smaller leak from the wellhead. And instead, if you cited the sensors maybe like this, you can distinguish between different sources. They'll confuse fewer sources, and you can see this on the right. The separator leak is no longer identified except for a little blip, and then the wellhead leaks are well within the 0.1 grams per second release rate. Now, I get asked a lot about sensitivity of monitors to height, and here I'm going to give the same answer. Height isn't as important as simply doing the measurements in the first place, and there's pretty low sensitivity. In this analysis, Will Daniels, a student at Colorado School of Mines, looked at 14 large emission events. He defined these as events exceeding a 400 part per billion threshold for total VOCs for one facility for about 6 weeks, and then compared sensors placed at 5 feet and 10 feet. And what he found was that higher units did see higher concentrations, but those actually were explained by calibration differences. We've now updated our baseline calculations to improve these. And he concluded that that 5-foot height difference has a relatively low impact on observed VOC concentrations. Finally, I'll say that the response time of a sensor to an event matters. I'd call this the T90 time, or the amount of time that a sensor will respond to a given signal. This could be a function of physical construction. So for example, an electrochemical sensor that would tend to respond over minutes rather than seconds, like an optical sensor, or a monitor without a pump that might respond slowly and kind of act like a physical averager as the gas has to mix over time to reach the sensor. For big events, a slow sensor response time won't matter, except of course in quantification. But for smaller events, a slow sensor response time may result in not seeing the event at all, which here I'm illustrating by averaging our own data, which is a 1-minute average, by 3, 5, and 10 minutes. And once you start getting down to the 5-minute mark, you see that it's kind of difficult to detect the event. So, in conclusion, at Project Canary, we see that market forces are driving adoption of emissions monitoring technology in the natural gas supply chain. We see that continuous monitoring is an effective LDAR method to achieve emissions reduction. I find that sensor placement is not nearly as important as simply measuring in the first place, and that additionally, there's low sensitivity to sensor height. Additionally, mass emissions flux calculations can be sensitive to the sensor placement, but not event detection or threshold-based programs. And finally, sensor response time is important. So thanks, and happy to answer any questions.